This set of animations is about two different kinds of functions that are useful in statistics, and in situations that you will need to describe mathematically during this course. The first type of function takes values on the horizontal axis and assigns them to values on the vertical axis. These kinds of functions involve covariational reasoning because one varying quantity is mapped to another varying quantity. The first varying quantity is graphed on the horizontal axis, and the second varying quantity is graphed on the vertical axis. The second type of function assigns a next value to a given value. But, for this kind of function, it may not be easy, and it might even be impossible, to know the value of the nth term in the series. Remember, a graph can be thought of as a mapping from one collection of data to another. However, even in cases where a graph is intended to describe the mapping from one collection of data to another, neither of the two collections may represent a single quantity that is varying in some systematic way. For example, the mapping could be describing old prices and current prices of various grocery store items. So, neither the old prices or the new prices would involve a single quantity that is varying in a systematic way from one item to another. Changes in the price of two items may be no more closely related than the numbers on the uniforms of soccer players. But, for now, we will focus on the second type of function that was referred to at the start of this animation. These are functions that map one item in a collection to the next item in the collection. Next, you will see some examples that illustrate this point. Here, the arrows are pointing to the odd numbers. And here, the arrows are pointing to the even numbers. It's not difficult to figure out a formula or rule that gives the nth even or odd number. Try it. What's the 10th odd number? Similarly, the nth term in other sequences also are not difficult to describe using covariational reasoning. Several examples are given on the following screens. Here are several sequences that can be built up using the odd numbers. Here you can see how the odd numbers are closely related to the square numbers. And the square numbers are closely related to the pyramid numbers. Differences at one level are objects at lower levels. You can use these patterns to figure out what is the next pyramid number. Here are some more familiar and closely related number patterns. Next, some examples are given in which several different rules may exist for describing a series of numbers. For this example, you might notice that the first term skips one number, the second number skips 3 numbers, the third number skips 5 numbers, and so on. Or, you might notice that the first number is 2 times 1, the second number is 3 times 2, the third number is 4 times 3, and so on. Or, you might notice that the first number is 2, the second number is 2 plus 4, the third number is 4 plus 6, and so on. Or, perhaps you see some other way to describe the nth term in a series. This example is the famous Fibonacci sequence. Look carefully at this sequence, and find the rule to describe this sequence. Then ask yourself, is your rule a covariational function or is it a function that defines the next term to each given term? These graphs and tables show one reason why the functions that we have been looking at are important in statistics and in other situations where we need to describe things mathematically. As you already have seen, one thing that we will need to be able to do in this course is to define functions that fit a collection of data. And, in statistics, linear functions and polynomial functions are especially useful. In past examples in this course, you have seen how polynomial functions can result from multiplying linear functions or from adding monomial functions. And the table and graph in this worksheet show how polynomial functions also can result from accumulating functions. For example, in this graph and table, notice that f1 is a constant function. f2 is accumulating the values in f1, and f3 is accumulating the values in f2. Furthermore, they also show that f1 is the constant function, f2 is the linear function, and f3 is the polynomial function. Similarly, if you scroll down this worksheet, you see that if you start with any polynomial function and if you use a table like the one shown here to calculate differences between values at regular intervals, then the second column of differences always reduces to a constant function. What this implies is that, for many real-life situations that involve constant functions or linear functions, polynomial functions often arise as accumulations of the constant or linear factors. For example, later in this course, we may start with a collection of data about scores for students on a test. So, the graph may look like the bell-shaped pile shown in this graph. And we may want to find the probability of scoring lower than 25, or higher than 75, on some test. In the past, one way statisticians usually answered such questions was to begin by first finding a function that describes the general shape of this bell-shaped pile. Then, they calculated the area under the graph, between 0 and 25, or between 75 and 100. And finally, to find the probability of scoring in these regions, they compared the size of these areas to the size of the total bell curve. But, one difficulty with this method is that it depended a lot on how well the function actually described the bell-shaped pile. So, they often had to be very clever in order to estimate the size of their own errors. Today, it's often possible to use computational methods to avoid errors which result from mismatches between the shapes of the piles and the functions that are used to describe them. Nonetheless, even when alternative methods are used, the same basic lines of reasoning continue to apply to other methods of calculating probabilities. In general, in this course, we'll be finding probabilities by creating simulations of the situations we're investigating. And, when we create simulations, it will be especially important to be able to develop functions that tell productive stories that fit situations we need to describe.